Hello, we are the group number 16 and in this video we are going to make experimental characterization of a tube and shell heat exchanger. Heat exchangers are machines that allow the transfer of thermal energy between fluids at different temperatures, through a separating wall or through the interface of fluids. They are used in different processes and they can be classified by its flow arrangement: parallel flow, counter flow, and cross flow. For a correct characterization, it's important to know properties as the global heat transfer coefficient, so heat transfer coefficient of the tube and the shell sides must be calculated. For this purpose, there are different correlations obtained experimentally or from theoretical analysis. Logarithmic mean temperature difference method, the shell side analysis, and the Bell-Delaware are some of those correlations. In the experimentation of this project, the shell and the tube heat exchanger were used, plus a computer program that controlled the flows of both hot and cold streams. Also, the flow for hot and cold fluids with their respective percentage of opening. This process continued until almost all temperatures stabilized, and the data taken in that period are stored in a spreadsheet. For each temperature and flow, 3 points were selected between the range of our group for parallel flow and counter current flow. The following table shows the settings that the exchanger was used. With the data thrown by the program, the objective was to calculate the global heat transfer coefficient for the shell and the tube exchanger used. For this, three methods were used: logarithmic mean temperature difference method, LMTD, and it was also compared with the result of Kern and Bell-Delaware correlation. One assumption was that the method Petukov-Kirillov was used to calculate the friction factor for turbulent flows. Considering the obtained Reynolds values, it is shown that the flow is completely laminar. The Bell-Delaware method is also very useful because it considers the correlation of baffle leakage effects, baffle spacing and cut, variable baffle spacing, and outlet and inlet and bundle bypassing effect. Nonetheless, when carrying out the calculations due to the missing information, the overall value of all those correlations was assumed to be 0.6. Additionally, a falling resistance value is used when applying the Bell-Delaware correlation. The value was simulated to be 0 because it wasn't known. Since the exchanger has been used only with deionized water and it is practically new, the assumption is logical. Finally, the realization of the Bell-Delaware method required the value of the viscosity of the fluid that acts through the shell at circumstances attached to the wall. These conditions weren't known. Furthermore, the viscosity was assumed to be the same all over the fluid, but there is not enough information to know if this assumption is possible. Table 3 shows the results obtained with the Bell-Delaware and LMTD methods. It can be observed that the heat transfer coefficient has a higher value for the shell side. This could be explained by looking at the dimensionless numbers in the table 4, specifically the nozzle number, which must be higher for the shell side, but in this the tube side has bigger nozzle numbers, which means that the convention is more important. At the same time, velocity can change due to the shell diameter, the clearance between tubes, and the baffle spacing. Furthermore, the heat transfer coefficient increases with temperature. This is reasonable because the temperature makes the fluid more turbulent. It also must have larger values for the counter current arrangement. This doesn't happen within all the data collected, but it is probably because of mistakes during the laboratory and the assumptions made by the correlations. Looking at the LMTG in the table 3, it can be observed that it is larger for co-current. The result is inconsistent because theoretically counter-current LMTD is greater and more efficient. As shown in the next graphs, it can be observed that the inlet co-current delta is large, but it becomes small at the exit of the exchanger. This fact means that for the same inlet and outlet temperatures, the co-current flow will need more surface area than the one needed by the counter current. In the other hand, Kern is a simplified method and doesn't consider that the shell flow has complex flow patterns. The results obtained are shown in the table 5. In the Kern method, the heat transfer coefficient must be higher, but in this case, it is smaller, probably due to the calculation or assumption mistakes. It must be higher in this method because Bell-Delaware considered different flow patterns that affect the main one considered by the Kern method. In the result obtained by Kern correlation, the tube still has the smaller coefficient, which is consistent with the Reynolds number. It is greater for countercurrent arrangement as expected.